Was not here last week, as you might have noticed, and from mid of next week I'll not be here again. But I know Ofek replaced me. I know what you did with him. How were the lectures with Ofek? Good. Is everything clear? Has to be. Okay. Akshay, stand up. You have a tutor, Akshay, right here. Yes, so know him. We'll give you some tutorials and grade the homework. And if you have problems, then you can ask him as well, if you want. If you feel more comfortable asking him, then you don't have to stay the entire lecture. If you don't, you can stay if you want, but you don't have to.
Yeah, I'll stay for 10-15 minutes then.
Stay for 10-15 minutes, okay. Unless you want something to say.
No, I can say
Akshay's
whatever I have to
office.
say.
What?
I'll say whatever I have to say in tutorial, not now.
Okay. Akshay's office is 512, my office is 509. Right. That's well. That's me. My office is 509. Right around here. Akshay is 512. Okay. Not everybody speaks Hebrew, so this will be in English. English would not be your problem. This course. I'm going to do a recap on things that Ofek did. I'm going to do it fast. But the important thing is the following. This is really basics, and you must be very, it has to be very firm in your heads. So that's why I don't mind doing a little bit of overlap with what Ofek taught you. It went a little bit faster than what I'm normally doing. The important thing is that you understand. I mean, I'm sure that Ofek mentioned it to you. In this course, if you don't follow what I'm saying, within 2 weeks you will not be here, because you will not understand what we're talking about. It's very mathematical, it's very structural, and a lot of very delicate points around here. A lot of small things that look small, but if you're making a mistake, you have no idea what you're talking about. Okay? So you have to be very, very precise. So we start with the special relativity. You've all seen special relativity, and Ofek taught you special relativity twice, basically. Once in the astrophysics course and once last week. But the important thing is that you realize the language. Right? And again, it's a philosophical thing. Oh, should I open a Zoom and open a something here?
Check if the YouTube is working.
What? It's on the air.
The YouTube is working. It's live.
It's alive, so I don't need to do anything, right?
Maybe you want to have a meet. I don't know if it's working.
No, I don't think it is. I don't think it's a meet. Not that I know of. Okay. If it's anyway, it's being recorded. Okay, so the physics, in case you didn't notice, is an experimental science, right? Everything is driven by experiment. If you have a great theory, but it is not connected to real life, we call it math. Right? That's called math. That's not called physics. Physics, at the end of the day, is there to explain experiments. Okay? In physics, there is an experiment, and there is theory. What is a theory? It's an idea. It can be right and can be wrong. Right? How do we know? By the experiment. A good theory explains the experiment and gives prediction to other experiments that we did not conduct yet. Okay? If it's enough to have one scientific experiment, there's a difference between experiment and scientific experiment, that the results are in contradiction to the theory, then the theory is wrong, not the experiment. Okay? General relativity is an excellent agreement with many experiments. Otherwise, we would not be talking about it. I will add, likely, I will add a few lectures towards the end because we want to speak about cosmology, and we will not have time if it will shorten too much. Okay? And also, I'm giving you the full mathematics. I'm going to get to you in your face, right? I mean, sometimes we have to tell people to scan down, and it's just a hand wave story. So no, it's not stories. I'm going to tell you all the math, and you'll see how things are constructed. Nearly all the math. There will be a few things that I just don't think are necessary to get through all the entire details of the groups. Okay, what's the experimental basis for special relativity? Michelson-Morley. What did they say?
It's the same in all directions.
Right. What does it mean if the space it's in all directions? We have two observers, right? Blue observer. Then we have a red observer. Wait, not red. The red. A red observer, like that, which is moving, right? And the time t equal to 0 with the crest of light. It starts from here, ends up somewhere here, right? And we have that. Right? Where is the crest of light according to observer and the blue observer? Well, I told you that. Start at the t equal to t, equal t prime equal to 0, right? This is O, this is O prime. That's another thing, conceptual thing, right? In relativity, we speak about events. Okay? The event is independent of the observer. It happens there anyway. Coordinate systems, observers, we are observer, I'm seeing something. Right? I'm watching a soccer game. Somebody scores a goal. This is an event. If I'm sitting on one side of the match, I can say, oh, it's to my left. If I'm sitting on the other side of the stadium, I can say, no, it's on my right. Right? Who's right?
Both.
Both. Right? There's no contradiction. Right? We speak about an event. Something happens. The event is independent on the observer. So we have two events. What is the first event?
Light emitted.
Light was emitted. The photon was emitted. What is the second event?
The photon
The photon was observed or detected. These are two separate events. Okay? Now, I can say, without loss of generality, right? Now there are two observers, the red and the blue, that look at the same events. Two events, right? And each one has coordinates. Right? Because they want to describe. Now remember, the description is something that we do for us. Because it's easier for me to write down in my notes that something happens, when did it happen, where did it happen, right? So that I write down. Right? Remember that, that's important. But this is my decision. Right? I can say that the distance between two events is in meters, kilometers. If I was in the US, I would say maybe it's miles. That's my choice. It doesn't matter at all for the events. Right? So, without loss of generality, the first event, the emission of photon, occurred at, let's say, t equal t prime equal to 0, x equal to x prime equal to 0, right? This is a vector, three vectors. I will mention vectors with arrows, by the way. Three vectors. Second event, the photon crest reached a certain location. Right? What is that location? Oh, in fact, I told you that. No, come on, you know that. What is the location of the second event? That depends on the observer, right? So for the blue observer, it will be x, y, z, and t, right? In which we have x squared plus y squared plus z squared equals c squared t squared. Right? For the red observer, same. X prime squared plus y prime squared plus z prime squared equals c squared t prime squared. Right? Very clear. Now, without loss of generality, we said that, we've been plotting it, right? The second observer, the red observer, is moving relative to the first observer in the x direction. Right? So that means what? that x prime is different than x. What about y prime and z prime? They are the same. Y prime is equal to y, z prime is equal to z. So what does it mean from these two equations? And that
The t and t prime.
t prime must be not the same as t, right? Two observers cannot agree, do not agree on the time of events. Okay? Is there a problem? No. Who's right?
No.
Well, no problem. Why? What quantity do they agree on? The interval. What is the interval? It's the difference between two events. So in order to define an interval, you must have two events. Okay? Starting and beginning, right? So there is a delta here. Right? So the interval between two events, interval squared is, you know, this is delta s squared. There's a difference. Now there is a little bit of convention here. Minus c delta t squared plus delta x squared plus delta y squared plus delta z squared. Right? There is a delta here because it's the difference between the two events. Right? Z2 minus Z1, Y2 minus Y1, etc. Right? I told you all this, right? Yeah. I just want to make sure that you all, sorry, I'm simply right, but I want to make sure that you all, and you don't seem bored at the moment. And he showed you that this is connected to the distance function in Euclidean space?
Yes.
No, I don't need to show you. What?
That it's a generalization.
Yeah, it's the same thing. Mathematical structure is the same. And then we can speak about Lorentz transformation, right? And then there is the notation. Notation is very important here. I don't know how much of it went with you, right? So in order to describe an event, write it down because that's it. Event, right? It's very basic because relativity can be extremely confusing. Really. Which one is shorter in time, shorter in distance? It can be very, very confusing. The way out, not to get confused, is to think of things in terms of events. Okay? Events. Think of that, right? Always. Otherwise, you can easily get confused. Right? We're talking here about two separate events. That's important. So we have coordinates, right? So to describe an event, how many coordinates we need?
4.
4, right? Which will be?
X, Y, Z.
Right, and they're connected. So we said that these are coming in space, which we call
Flat space.
what?
Flat space.
Minkowski space. Right? Not exactly flat. There is it's not a Euclidean space. So Minkowski space is different, there is a minus sign. Okay? And then we said, okay, so you have T, so each event is described by 4 coordinates. Who determines the coordinates? Me or you. Do the event care about the coordinates? No, it will happen there anyway. Coordinates are for me. Okay? Now, so normally it will be T, X, Y, and Z. How do we write it?
X0, X1, X up.
Right. But it's 4 vector X, mu of X showed it to you. Right? Upper index. The location of the index, I don't know if Ofek emphasized that, extremely important. You don't put the indices where you want, you put them where they need to be. So it has to be upper index. Okay? So x0 is ct, x1 is x, x2 is y, x3 is z. We're going to use most of the Greek alphabet. So if you're not familiar with the Greek alphabet, this is a good time to review your knowledge. Okay? Latin indices are normally used to describe just the spatial part when we need them. We will need them when we're talking about cosmology. Okay? Except for that, in this course, we will not make use of them. And then Ofek introduced to you this matrix. Let's do lower indices, eta, mu, and nu. which is a very simple matrix. Minus 1, plus 1, plus 1, plus 1. On the diagonal, everything else is 0. Right? It has a name. What's the name of this matrix?
The metric.
It's called a metric. Now, a word of caution, metric. It's not just it's a simple matrix. You don't need to worry about that. I also took the course in particle physics, and also those who will take the course in quantum field theory. Right? You see the same matrix nearly. What's the difference?
The sign.
The sign, right? There is a difference in sign. It's a convention, right? The sign is a convention here. I'll just write down that at mu nu QFT, there is a plus 1, minus 1, minus 1, minus 1, everything else is 0. Why? Just because, to make your life more miserable. It doesn't really matter as long as you keep on the same convention. Then, how do we write the interval using this matrix and this new short notation?
Just like mu times SNU times the
And an interval that squared. So what is written in there is just sum mu and mu 0, 3 delta mu delta x mu delta x mu. How many terms are there here? 4. How many terms? 16. Right, I'm summing over mu and mu from 0 to 3. 0, 1, 2, 3. 0, 1, 2, 3 times 0, 1, 2, 3. 4 times 4. There are 16 terms here in this equation. 12 of them are 0 because the matrix is 0. Okay? So you're only left with 4 which are non-zero. And then he showed you there is the Einstein summation convention. It says that, what did that say?
We drop the summation.
We don't need the sigma.
We don't need the sigma. Every time we're saying an equation that contains on the same side upper index and a lower index, we understand that we're summing over them. We don't need to say anything further. This is also called what? I don't know if I've told you.
Contraction.
What?
Contraction.
No, it's not contraction.
No.
What?
Vectors and covectors.
It's called a dummy index.
Ah.
Okay. This is a dummy index. Okay. They have to appear in the same side of the equation twice. Once as a lower index, once as an upper index. Can the same index appear 3 times in the equation on the same side? Only if you make a mistake. And it will be a big mistake. So if you run into something like you get some calculation, you end up with mu more than twice in one side, that means you did something very wrong. Okay? Well, that's what you get. Okay. What is the Lorentz transformation?
Transformation that conserves the
Right, the transformation that concerns the interval. Which type of transformations you have that concerns the interval?
translation.
What?
Rotation. Translation. Rotation.
Translation, right? What is translation?
Just
So Lorentz transformation. Right? Any transformation that conserves the interval. That's a definition. Right? The options, there are not that many, they make a group. I don't know if I showed you that, it's called a Lorentz group.
Except the translation.
What?
Without the translation.
You what?
Without the translation.
Without translation. Which translation is called point, correct? So translations, x mu, that's another notation. X mu goes to x mu prime, which is x mu plus some constant. Why did I put the prime on the mu? Why did I write x mu prime and not x prime mu?
Because
The index
coordinate.
It's the same
same
coordinate.
the same vector.
Same vector,
Same
different coordinates.
thing.
Because what if I put mu equal to 2, then x2 is y. So I want to write y prime, right? Y prime is x2 prime, right? Yeah, you're all with me? Small things, but they make a huge difference. That's why I feel it's okay to repeat things that I've already said, just to make sure that they're
What's
all
the
the same.
difference again?
What?
What's the difference again?
I said mu equal to 2,
Yeah.
right? x2 is y.
Yes.
Right, so if I want to write y prime, I would write x2 prime,
Okay.
right? So that would be x mu prime if I'm generalizing it. Right, x mu prime. X prime 2, I'm not sure what it means really. I don't really know what it means.
Square.
What? Yeah, maybe x prime squared. I don't know what is x prime. Yeah. Question? No? Okay. So we have, this is a translation, and then we have rotation, and we have a boost, right?
And it's flips.
So the general, that I'm sure Pep also showed you, general Lorentz transformation would look like x mu prime is equal lambda. Now what am I going to do with the indices?
One top, one below.
What's going to be here?
Me,
The prime.
Mu prime,
and at the bottom, to the right, is mu.
bottom to the right. There is a space here. This is empty below that. And here I can do something, whatever I want. So I can put a mu x mu. Why can I put whatever I want?
Dummy index.
Because it's a dummy index. Right? If it's a dummy index, then I can call it whichever name I want to call it. Right? It's very important to keep this space here. It's not one on top of the other. Okay, only place where you're allowed to put one on top of the other is when?
Delta.
It's the Kronecker delta function. Right? Otherwise you don't do that. So there is a space here. Keep on the space, it's important. Then what's the condition for any transformation? This is right lambda, right? Any transformation to be a Lorentz transformation? I showed you that. Bit of math.
New.
Right, we get eta. So condition for a transformation to be a Lorentz transformation, right? Eta rho sigma is lambda mu prime rho lambda mu prime sigma. Eta mu prime sigma mu prime. How many equations are written on the board?
16.
How many terms in each equation?
16.
16, right? See that? There are 16 equations here. Why? Because rho and sigma, these are not dummy indices. Rho and sigma are not dummy. They are real indexes. They appear both in both sides of the equation. The dummy index appears in the same side of the equation. Right? So rho and sigma goes from 0, 1, 2, 3. So there are a total of 16 equations here. And each of these equations, so I choose one equation, right? Rho will equal 1, sigma equal 1. That eta 1, 1 is equal lambda mu prime 1, lambda mu prime 1, eta mu prime mu prime. How many terms in each equation? 16. Because mu prime and nu prime have going from also 0, 1, 2, 3. Right? So total 256 different terms written here. It's great for a computer. It's much less fun when you have to do it by hand. Questions? No, did Offer shows you these examples?
Yes.
Rotation and,
Yes.
and boost. So skip that part.
Showed us a lot of transformations, or we start with transformation rules for vectors and.
I know how much you did. I just want to make sure that you understand what you did. I mean, I could start exactly from the. I know exactly the point that you went to. I want to make sure that you understand. If you think that I'm just wasting your time, tell me, and I just jump. Am I wasting your time? Somehow, nobody complains. Guys, there is a reason why it's a review, right? But there is a reason why I do it. You have to know these things. It has to be, it will be, right? If it will not be, it will not be here. You have to be, this is a language. We're speaking, we're learning the language now. Yeah.
Can you explain more about the gap in the lower index?
Yeah, you'll get it. You'll get it. So Ofek told you that, no? It's part of what the material covered. I will talk about it. It's crucial. Right now, just you don't have to understand it, you have to write it. Okay? But you'll understand it very shortly. Okay, so we have the rotation. I mean, a real rotation, not methodical, right? But a rotation in Euclidean space is legitimate Lorentz transformation. Right? If I'm rotating around the z-axis, it's fine. So it's a very fair Lorentz transformation. Also, transformation when one of the coordinates is t,
then it's hyperbolic.
then yeah, call it a boost. Right? That's identical to what you've seen. This is what you're used to with Lorentz transformation. Right? That's what we call a boost. And Ofek showed you that. If I just go over it very quickly. Right. Boost in x direction. Just the transfer. It's just the rotation between the time and x, right? So lambda u prime nu is cosine hyperbolicus of phi minus sine hyperbolicus of phi 0, 0 minus sine hyperbolicus of phi cosine hyperbolicus of phi 0, 0 and then 0, 0, 0, 0, 1. Okay, and again, apply that. You have 16 equations. Each one will contain 16 terms. And you see that it's okay. And then you'll end up with CT prime is CT cosine. Alright, CT x, y, z. CT prime is CT cosine hyperbolicus of phi minus x sinus hyperbolicus of phi. X prime is minus CT sine hyperbolicus of phi plus x cosine hyperbolicus of phi. And then you just define beta to be V over C, which is tan hyperbolicus of phi. And gamma is 1 over square root of 1 minus beta squared. So it's cosine hyperbolicus of phi, gamma beta sine hyperbolicus of phi, and you end up with CT prime equal to gamma CT minus beta x, and x prime is gamma x minus beta CT. You've seen that. So this whole formalism gives you identical results to the results that you've seen in special relativity. Any questions? No. Next. Time dilation. I've showed you that as well. What is time dilation?
Looking
What is proper time?
Proper time is the time between two events of an observer that moves from one.
doesn't experience
Interval divided by
just in time.
What is proper time then?
It's the time that you feel, it's the time that the objects feel.
It's the time in your reference frame.
What time?
It's the time in my local frame. Right? I'm holding my clock, right? And I'm walking. Right? I like to walk in the class, right? What about the clock? Is it moving with respect to me?
No.
No. Right? My clock is not moving with respect to me. Now you see me walking and you see my clock walking or moving. Clock doesn't walk. Right? But it moves. But relative to me, my clock is attached to my body and I am moving and it moves with me. That's a proper time. That's the time that the manufacturer of the clock meant it to be, assuming that the clock is okay. Right? It doesn't, so that's called the proper time. Okay, so the proper time but 10 is no longer proper. Right. Proper time that's the time as measured, we say, by an observer. The technical term is co-moving with the clock. Co-moving with the clock, i.e. that does not see the clock moving with respect to it. Right, so observer O, what does it mean does not see the clock moving with respect to it? Delta x equal delta y equal, remember, events, right? What's the difference in distance between two events? 0. Right? So, distance interval between two events. Right? So, delta tau squared is defined as minus delta s squared over c squared. So minus 1 over c squared, eta mu, delta x mu, delta x. Now, you are watching me and you are seeing my clock moving. What would you say?
Delta x, delta y, delta z is not
Right, so delta tau prime is delta t prime squared minus delta x vector prime squared divided by c squared to the power 1/2. So we have 1 minus beta squared 1/2 delta t prime. Now, Aufek mentioned that to you in the first. We are now making the assumption that both observers are in inertial coordinate system. You want to understand what it means?
Yes.
Yes? Is there anybody that does not understand what it means? Right? Because we'll deal later on with non-inertial coordinate system. Right now it's only inertial. Right? Inertial coordinate system, what do we get? Oh, you know that. What? Interval is conserved. I should have mentioned that, right? But only in inertial coordinate systems. Right? So we have delta tau, inertial, both observers are in inertial coordinate system. Namely, they don't have acceleration. We have the delta tau prime is equal delta tau, from which we deduce that delta t prime is 1 minus beta squared minus 1/2 delta t. What do we call that?
That's kind of, yeah.
What?
Yeah.
Gamma. And what can you tell me about gamma?
Because
It's always greater than 1. Right? Yeah.
Question about inertial coordinates. Like
Yeah.
if I think about it, if the frame of reference moves with a constant velocity relative to another frame of reference, that is inertial.
That is inertial frame.
So, but there is still this problem that you need to set one inertial frame, and that will kind of determine which of the other ones are related.
No.
So
we don't have to. That was Newton's basket thing that I talked to you about. No. I don't need an absolute space right now.
Okay, so how do you define an inertial frame regardless of some one system?
Right now I'm just saying a system is inertial. That's it. I don't have an absolute inertial frame. We'll get to that. Okay? He talked to you about Mach's principle, right? That inertial frame is something which is relative to the distribution of mass in the universe. Right?
I feel like Mach's principle suffers from the same kind of problem.
Right now we don't need it. You'll see it will come down. It will come down in 1 or 2 weeks. You'll see where it will fall. Hopefully by then things will be easier. Right? Everything I said is clear to everybody, right? So I don't need to spend more time on it. If you have questions, ask. I'm very serious about the thing. This is very quickly things will get blurred in your mind. You have to have the firm basics, because then what you'll do is you go back and you get that. Right? So it has to be very, very clear in your mind, these things. Otherwise you get lost. Okay? So yes.
What does delta tau prime represent just in reality?
No, the prime is just to saying that this is delta tau as would be viewed by a blind observer. In reality, this doesn't really mean much. It's just the delta s. It's the interval. Right? We said that two observers would agree on the interval. And if I define delta tau as minus delta s squared over c squared, I can define delta tau prime. It's the same as the prime. That's all. But physically, you're right. This is bad notation, because delta tau has a physical meaning. It's called the proper time. Delta tau prime doesn't call it. More? No. 4 vectors. That's where things get more complicated and more interesting. Right? I use that without saying that. What did Ophir tell you about 4 vectors?
Transformation rule.
What?
Transformation rule.
That's?
They transform with the
Yes.
Yes. What can we say about vectors? Let's start from the first thing first.
They live in a tangent space.
What?
They live in a tangent space.
What? Yeah, okay, they live in a tangent space. What is a tangent space?
It's defined from a manifold and a point. It's all the vectors.
Now we did not define what is a manifold, but
Yes.
we will define it later on. The important, right? So that is right. The idea is that the spaces are not flat; they are not Euclidean. Right? They are curved. And then when you have a curved space, how do you exactly define directions? How do you define what is the shortest path between one point to another on a curved space? Right? So the first thing we start with is defining vectors, and they belong to the tangent space to a point. And when we have 2 different points, you'll have 2 different tangent spaces. Right? So if I have some sort of a manifold, and I define point P and point Q, right? And I put the tangent space to the point P, the tangent space to the point Q, they are not going to be the same space. Right? And how do we connect from P to Q is a different question which we will solve. Right? Now all the vectors that go through P, they really define a tangent space which we call TP. All the vectors that go through Q, they define a different tangent space which we call TQ, right? So the vectors really belong to a given point in space-time. Of course, in Euclidean space, you don't know that. You don't care because the space is flat. In real life, we care a lot. Real life in GR, which you can argue whether this is real life or not. Okay? Now, what's the definition of a vector?
Something like it's transformed like a vector.
Does the vector transform?
No.
The vector doesn't care. Remember, one of the basic entities in relativity, there is a discrimination. You have to think that's a very deep point, right? There is a discrimination between the real life, what really happens, and how we choose to describe it. The vector is there, right? But how we describe the vector is our own problem. The vector doesn't know and the vector doesn't care. Okay? We can say, we put coordinates, and we said, okay, we have a vector components, v1 and v2. But that is my choice. And your choice can be very different than mine. You can say, I actually would like to have my coordinate like that, and that will be my v1 prime and v2 prime. Does the vector even know about that?
No.
Does the vector care about that? No. Right, so what happens to the vector when we're changing frames?
It stays the same.
Nothing.
Nothing happens to the vector. What changes? The description of the vector. We change the coordinates, and so we change the description of the vector. Okay, that's the crucial part here, right? It's a description that is changed. And so the definition of a vector,
Something that transforms.
yeah, it's an abstract entity, right? A vector is something which is completely abstract.
Element of the tangent space.
Connects to
What?
connects to points maybe.
The what?
Connecting to points maybe.
I did no. Vector does not connect anything.
Element of the tangent space.
What?
Element of the tangent space.
Yes, it's a metal tangent space, that's right. Because
Is
the
that
set
what-
of all vectors would form a space, which is a tangent space. So the vector is an element. But the correct definition of a vector, which is something, since when you've been dealing with vectors, but finally you're given the correct definition of it, is an abstract entity whose components, namely the description, is transformed in a certain way when we are transforming our coordinate system. This is the definition of a vector. Okay? I don't know what you were told, but finally you can put a check on that part. Right, so a vector, it's a 4-vector, right? So it has 4 components. Actually, it's true for any vector space. It doesn't really matter. So we call these 4 vectors because we work in 4-dimensional space. So any quantity, a vector, is a correct thing is contravariant 4-vector. Be really precise. That's what we define here. A contravariant 4-vector, which I will always call it a vector for short, but you should know that that's what I mean. Contravariant 4-vector is an abstract entity whose components whose components undergo the transformation V alpha goes to V alpha prime, which is lambda alpha prime beta, V beta, when the coordinate system is transformed like, say, x alpha goes to x alpha prime, which is lambda alpha prime beta, x beta. That is a definition of a vector. From here on, you know. Okay? The vector is how many, well, we work in 4 dimensions, so how many components will it have? 4, right? There's infinite amounts of, and now the other thing that which I said and emphasize, and often tell it as well, the vector belongs to its point, is defined only at one point in space-time. You cannot just take the vector. I mean, you plot the vectors with arrows, right? I don't know what you thought about that, but you could, move the arrows as you wish. No, I mean you can, but in real life it will be meaningless unless you define exactly what you're doing, and we will see how to move a vector from one place to another. For example, when we need to take derivative of a vector, it's going to be quite. I have to think a little bit how to do it. All right, questions? Should we go faster?
Yeah.
Still the review, yes?
Yes.
What? I have to make sure that you know that, because if you get stuck on that, I'm going to lose all of you. Wait, okay, if you said it, you know that. If you know, then you know. Then we said all the vectors belong to the time and space of P, so let's go TP, we plan that. All the vectors form a vector space, the set of all vectors. The set of all vectors through a point P forms a vector space, namely if A and B are scalars and B and W are vectors, then we have A plus B, B plus W. Normally scalars are write with small letters, vectors as usual. I don't need to put the extra vector. B plus W is a V plus BV plus a W plus BW. And it contains everything you know from linear algebra about vector spaces. Yes?
I have a question. If our tangent space is 4-dimensional,
yeah.
What dimension is the manifold?
What dimension is?
The manifold which they exist on.
4-dimensional.
Aren't the tangent spaces to n-dimensional manifold?
To a certain point. Yeah, the manifold will be 4-dimensional. There are higher theories,
That's
like
how
in
we
string
define
theories.
it.
But
Isn't it how do you define the dimension of the manifold?
yes, but there are higher level theories, like string theories, you get a higher dimension. Right now, everything is 4-dimensional.
And we don't embed the manifold in some higher dimensional space, right? We treat it as a
Depends on what theories you want to work on.
What?
Again, if you want to go into string theories, then the manifold will be higher dimensions. Right now, we stick to 4 dimensions. Okay. If it's a vector space, then there are bases. How many bases can we choose? Infinite, right? We choose. Right? Now, okay, those of you who study math would be easier for them. Those of you who are a bit less, then it might be a bit more tricky. You still have to know that. So, we set the basis for 4 vectors. Basis. Basis of the Daniel space. TP. Right, so you know what is a basis, right? Any set of 4 vectors that do what? Span the space and right? Linearly independent. And how many of these we have? Infinite number. How many vectors will be in each basis? 4. Yeah.
You don't need all the conditions.
What?
You don't need all the conditions. You can, if you have 4 vectors span the space, then are they?
No. They have to be. I have to have a set
There's a
of
set.
independent. I have to have a set of 1 vectors that span the entire space, and 2 they have to be independent.
And determine and the
The
theorems
4 The 4 is because the dimension of the space is 4. I can always find 4 such. But it doesn't mean that any 4 vectors will be independent. Right?
Any four vectors
who
that span the space. will
Every
be
sperm
independent.
that is a theorem in algebra. Right? The other thing which I emphasize, and I emphasize again, I do not need the coordinates to define the vector. The vector is there. I need the coordinates for me to to do calculations, to describe the vector. But the vector doesn't need it. Okay? Physics doesn't need us. It will still be there even if we're not looking at it. So we can set a set of 4 vectors, which will be span the space. So a basis of 4 vectors. Again, there is a very delicate notation here. I don't know how much of it went to do. How do I describe a basis vector? Right. So I put exactly. So I put E, that's a basis, and mu. But that is not. Why did I put this the parenthesis? Because
it's not a component.
It's not a component of a vector, right? When I wrote v mu, I meant the components of the vector mu. Here I mean a set of 4 different vectors. Okay? It's not the same thing. It's 4 different vectors. Each one of them will have 4 components, of course. If it's a coordinate, it will just be, coordinate basis 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, etc. Yes?
Why it has a lower index?
Second. First you see that I'm allowed to write it like that. Because it's a set of 4 different vectors. Okay? Why? Now I'm going to answer your question. Why? Why do I put it like that? Because I want to use Einstein's summation convention, right? So if I have a vector A, and I have a basis, A mu, how do I describe the vector? A mu, right? This is a basis vectors. And this is the component of the vector A in that basis. Yeah? Again, it's subtle, it's easy to get lost. And of course there is a sum. Right? Mu goes, how many values?
0 to 2.
0 to 3, right. Mu goes from 0 to 3. Okay. What are A mu? So when I'm saying A mu, what does it mean? The component of the vector A. What?
In a specific basis.
Yes, in a specific basis, right? Okay, now I don't know if I often showed it to you, right? I sort of erased that, right? When we have a space, whatever space, right? The standard example is a tangent vector to a curve, right? What we can do if we have like a general manifold, you can always draw a curve along this manifold. Right? How do I specify the location in that curve?
One parameter.
I set a parameter. So I just start to walk along. It's like I go on a hike. I have a trip, and then I say, okay, this is lambda equal to 0, lambda equal to 1, lambda equal to 2, whatever, right? I go. That's basically the only way I can do that. I just have I'm going on a trip along this curve, and what I can specify as a vector would be what? A tangent vector to the point on the curve, right? Now, so this is a general curve, general pass through space-time. I'm going on a trip to Alaska. I'm just going there, carry my tent with me, everything is with me, and I'm going, I choose some path. Right? Now, I can specify the coordinates. Right? We didn't really speak about the manifold, really what it is. Maybe I should say that loosely. What is a manifold?
Closed space.
It's a space, yeah. It's what defines this space? What is the unique thing about this space?
Metric.
What?
A metric.
No, metric is something completely different. We don't need a metric for a manifold.
It's closed.
What?
It's closed.
No, it doesn't have to be closed. What?
It has a mapping to R something, to to R4.
Nearly. Nearly.
Continuous mapping.
I'll go something which is much simpler than that.
Locally, it's the same as a
Right.
Euclidean space.
It's locally Euclidean. It's globally it's not Euclidean, but locally it is Euclidean. Right? When we think of the surface of the Earth, right? The Earth, the surface of the Earth is not Euclidean. Right? If you try to draw a map of the Earth, right? Often shown that sure, right? If you have to try to draw a map of the surface of the Earth, right? This is a Euclidean two-dimensional space. The surface of the Earth is two-dimensional, but it's not Euclidean. We cannot map it one-to-one to a board. We always get stuck in at least one point, right? So what do cartographers do when they draw a map?
Stretch.
Yeah, normally they take 2 points and they stretch it. The 2 points will be the North Pole and the South Pole. That's why Antarctica looks always very big on the map. It's not that big, it's just the way this, right? This is a manifold, right? So a manifold, without getting into the math, I'll get into the math if you want to. I don't know if we should because we have a short semester, right? But it's there in my notes, so we can go over it. Maybe Akshay will go over it, right? A manifold is a space that globally is not a Euclidean space, or doesn't have to be a Euclidean space. Locally it is. So if we zoom in, it looks flat. Yeah.
Any manifold or specifically?
Any manifold. This is the definition of a manifold, right? Namely, I mean, this is a manifold. This is not. Right? It's not a porcupine. A porcupine, right? You don't have spikes. You don't have, something that looks like that. Okay. Now this is a, mathematicians will know that. So we are physicists. This is the Department of Physics. We're physicists, so we only work with nice things. We don't care about these, strange spaces that mathematicians may like, right? We don't. Here in physics, we do something simple. Now, again, the thing in your head, the manifold that we're talking about, all the spaces that we talk about, are globally they are not Euclidean, but locally, if you zoom in close enough, they will look Euclidean. Right? Flat earthers take the opposite. They think that if it's locally Euclidean, then everything locally flat, then everything has to be flat. Okay, which is not okay. What can I do? Yeah, questions. Yeah.
It will be locally flat with odometric, not Euclidean.
It will locally Minkowskian. When we talk about four space-time, when we spoke about space-time, 4 dimensions, it will be locally Minkowskian.
And it's in a manifold.
It is a manifold. Yeah. Minkowski is not Euclidean because there is in the metric there is this minus sign. It's called a Lorentzian manifold.
So we just need a specific metric.
We don't need a metric. The definition of a manifold is more general. Metric is you can have a manifold without a metric. Again, you're getting into math. There is no point. We can go into that if you want, but we take us too deep and too far from what we actually need. It's going to be complicated enough right now. Okay? You can see how deep we can go, and it's very deep. But there is no need, because then we go into more math and we're going to stuck with physics. Stick to physics. Okay.
How do you define flat space?
What?
How do you define a flat space with it?
There is no such thing as flat space. There is a Minkowskian space. That's what we're doing in this place. I just defined it. It's the atom unit. Slowly, all these questions will be answered. Yeah.
So if we think about space-time, right? So it's a 4-dimensional manifold.
Yeah.
It has to be locally homomorphic to Minkowski space.
Yes.
I'm not saying anything.
Yes. I'm talking about this manifold Euclidean, but yeah, the idea in 4-dimensional would be Minkowski. So, how do I define that? Why did I say all that? Right? Because it's locally Euclidean, so I can always define a local coordinate system. Okay, you're with me? I mean, the coordinate system I will define here, right? This is 2-dimension, right? So I can put like a 2-dimension coordinate system. The coordinate system defined here may not be the same because of the curved space, but locally it's okay, right? You can always define locally Euclidean, locally coordinate system because it's locally flat in this 2-dimensional space that I'm drawing here. Again, think of the surface of the Earth. right? Globally, it's not Euclidean, but locally, it is. Okay? In this classroom, you don't have any problem with me drawing x and y. But I cannot extend that to the entire surface of the Earth. Right? Good. So I can define the tangent vector to the space, right? V mu. How will I define it? Tangent vector, sorry. This is tangent vector to a curve. Tangent vector to a curve will be a what?
Derivative.
Derivative of what with what?
The derivative with respect of the parameter. The location with respect of the
Vx mu over V lambda. Right? I'm progressing along lambda, right? I'm progressing along the curve. The curve is described by this parameter lambda. Right now I'm at lambda equal to 4 and I'm progressing into lambda equal to 5. Right? So my tangent vector is how the coordinates change when I progress along this curve. This is a tangent vector to a curve. We're going to encounter that quite substantially. Sure. Here? Yeah.
Those would be just the basis vectors? Or the
No, there's no basis vector. The coordinates will be whatever I choose. Okay. What is the entire vector? If I want the entire vector V, then I need to have the basis, right? V mu, E mu. Yeah.
What is x mu here?
X mu would be the coordinate. Right? I specify here coordinates as I want, right? I can put the coordinates like that, I can put the coordinates like that. Yeah.
just bigger?
What? Second.
Yes, a question. That lambda, that parameterization, doesn't it have to satisfy certain properties?
The only property is it has to be increasing along the curve. It's the only thing. Increasing, monotonically increasing.
Isn't there something? Doesn't it have something to do with kind of the speed with which it?
It's just the way I specify the curve. Nothing to do. It's my choice again. I have a curve. I just want to know. I want to tell you, right? I show you a map of where I'm going. I'm going now on a hike, right? I'm giving you a map of where I'm going, and then just that you know where I am, I just say, okay, I just put the. I mean, this is my trip, right? There is a mountain here, and there is a lake, and I'm going to be going along this direction, and then I'm just going to tell you, right? Now you call me on the phone. Where are you? Well, I'm on the same path that I told you. Now I'm at point lambda equal to 4. Then you know where I am. Right? I just specify. But that is my choice. It's completely my choice. There's nothing, nothing physical about that. You all with me? There is a reason why I spend a lot of time on that. Although I know I already spent some time into it. Right. These are the coordinates. If I make a Lorentz transformation, they will change. Just fine. Now, the transformation of the basis vectors. Again, I think that you've seen that, but let me just hear. What will be the transformation of the basis vectors?
Lower than inverse.
Inverse Lorentz transformation, that's right. Right, you all see that?
Yeah, it's a big component.
What?
Overshoot.
Overshot me right there. So transformation laws, transformation of basis vectors. Right? The vector V is V mu E mu. What happens to the vector when I make a Lorentz transformation? Nothing. Right? So it's equal to V nu prime E nu prime. But V nu prime, I know how to specify it because I already specified it and just erased it. How it transforms, it's lambda nu prime mu. V mu E and nu prime. From which we get that E mu is lambda nu prime mu E nu prime, which means that if I want the new basis in terms of the old basis, I need to inverse Lorentz transformation, And that's one asked me, why do I keep insisting putting the space here? Because how do I write the inverse Lorentz transformation? Inverse Lorentz transformation is a Lorentz transformation by itself, just going in the opposite direction, right? And I'm going to write it down with the opposite. So lambda minus 1 nu prime mu is lambda nu prime mu. Now the first index is lower, the second index is upper. And so we have E nu prime is lambda nu prime mu, E mu. Yeah.
Vectors themselves change in here.
Oh. Vector did not change. The vector is the same vector.
No, I mean the basis vectors themselves change.
Yeah. I wrote this vector as components in one basis.
Yes.
The basis did not change. I selected. It was my choice. I selected this basis, and you selected that basis. So when I measured the vector, this was the components of the vector in my basis, and these were the components of the vector in your basis. The question that we ask is, okay, how do I, if I given my basis, or how do I know my basis, how do I transform to your basis so that we can talk? And this is the answer.
So these are different vectors.
No, it's the same vector.
No, I mean the basis vectors are the same, different vectors.
These are different sets of basis vectors.
Okay.
One I chose, one you chose. And this tells me how do I go from my basis vector to your basis vector. Okay? It's important. Yes?
Where can we see the basis vectors in the picture that you put there?
You cannot. You cannot, and it doesn't really matter. You've seen it short. Okay. But now comes the thing that, why do I say that? Right? That this is because, again, the next step is because we're getting more and more abstract, right? So the covariant vectors and the dual spaces, right? So you've seen dual spaces. Also, I've talked about dual spaces. What is a dual space?
The dual space is the set of a linear function from the vector space to the scale.
Say it slower.
It's the set of all linear functions from the vector space to the field, to the scale.
It's not functions, it's functionals. But
Bilinear
it's
functional.
it's
Yeah.
okay. It's a set of transformations, basically. Right? Covariant vectors in dual space. Dual space. Right? So if TP is the tangent space, let me say TP star is the cotangent space, or the dual space. Which consists, TP star consists of all linear mapping or linear maps from TP to R. Things get more abstract because I'm looking at it as namely, if omega belongs to TP star and V belongs to TP, what does it mean?
Omega of V is
Omega that works on V belongs to R, the real numbers. Okay. This moment there is no. I don't have in my tip of my head a good example, but there is a good example. But I'll show it to you in a second. Of elements of the cotangent vector space, and of course this is in a linear way, right? So omega that works on AV plus BW is omega A times omega that works on V, or operates on V, plus B omega that operates on W, and that belongs to R. Okay, and then, so again, the same way as I'm thinking of a vector as an abstract entity whose components transform in a certain way, that's the same way that I'm thinking of omega as an abstract entity. And that's the mathematical definition of it, right? It's an abstract entity that when it works on V, gives me something, which is a number, real number, right? The thing in your head, which you saw many times, right? Row vectors versus column vectors, right? You have a row vector and a column vector, V. That's why I always describe it with V would be column vector, and omega would be row vector, right? And omega that operates on V is what? Is exactly what you're used to from multiplying a row vector with, right? It's just exactly omega 1 V1 plus omega 2 V2 plus omega 3 V3 plus omega 4 V4, which is a real number. The other thing that you saw already, that you know, but that may be a little bit more tricky if you're
Dual space.
What?
Dual space.
Yeah, well done. I didn't say that. Yes. I try to give you things that you have it in your head, that it will be stuck in your head properly. So how do you think of these things? How do you think of these elements? Because it's going to be crucial. The next thing we're going to do, which often did not do, is to define tensors. But right, so before we define tensors, we have to define that, right? Omega of V, other things which you've seen in quantum mechanics, bras and cats, right? I don't know if you've thought of that, right? They don't live in the same space, right? If you have a Dirac bra, psi, right, and a Dirac cat, will live in a different space. Sorry, this is a cat and this is a bra. This is a cat, right? It's an abstract description, right, of something that lives in where? Hilbert space, and that one, the dual space, right? And what happens when phi is acting on psi? What do you get? A complex number, right? But it's the same idea. It belongs to some complex, to the complex number, right? It's the same idea. Here we just have real numbers. We don't need complex numbers. Okay? Important thing, they don't live in the same space. They live in a different space. Right? So you cannot add them together, right? One can operate on the other, but not the other can operate on the first. But they do not live in the same space. Right? Now,
so,
yeah.
A question about the definition of the scalar. Is a scalar just a new real number, or is it something that's invariant under Lorentz transform?
Anything that is invariant under Lorentz transformation, but we're going to get to that definition shortly. We'll do it today. If you feel that you learned something new, and I just don't repeat what Ofek said. This is just to have these things properly stuck to your head. Right, and then so we can introduce the basis vectors for omega. So we can write down omega as omega mu, and then the basis vectors will be theta mu. Again, the same as we had for E. This is a set of 4 basis vectors for objects in the cotangent space, and they are easily defined by what happens when theta mu operates on E mu. What do we get? Delta. Delta is the only thing that I can write as only thing I can write with the upper and lower indexes on top of each other. Delta mu. Okay. And elements, this omega is called cotangent vector, covariant vector. Or in short, I'll call it covector. So there are vectors and covectors. Another name, if you're familiar with the math, this is called one forms. Now there is a whole theory of P-forms, it's called, which makes some of the calculations very easy, but I never have time to go over that properly. Just that you know this is part of what's called P-forms. Then if you encounter that, you know it exists.
Yeah.
Yeah. I'm not lying. There is something like that. We can go over to that. No, we cannot go because we don't have time. There are some things which are quite good for it. Mainly calculate determinants and volume functions. Now, the reason why we don't write the basis vectors, because we don't need that, because of exactly that, right? Because if I want to look at how omega operates on V, I can write it down as omega mu. This is the components, V mu. This is the component I don't mind. I can just change the order. And then I have the actual vectors, right? Theta V mu. Theta mu that operates on E nu. So this is of course equal to omega mu V mu delta mu nu. So it's just omega mu V mu, which belongs to R. So because of that, I don't really, because I have this delta function here, I actually never write the basis vectors. So that's why you don't see them, because I don't really need them. And then of course V of omega is defined as omega of V, which is also omega mu V. This is different than the plot I just drew you of row vector versus column vector, because I can also do the opposite and it can still work. Yeah.
It's the thing from the natural isomorphism, right?
Yeah. Yeah, take a bit like that, that's fine. Okay. So we have this example. The final example that I don't know if Ofe gave to you is the gradient. What is a gradient? What is a gradient?
How?
It's the largest.
I have a scalar function phi, right? I have a map here, and there is some function phi which is defined everywhere. Like height function, right? So in a map, there is a height function. Right? What will be the gradient of the function? It's the partial derivative with respect to the space-time coordinates, right? So the gradient of phi, which I'm going to write, gradient is defined as d phi. Did Ofe show you that? No, that's how much you look. Okay. D phi is. Did he give you these examples of bras and cats?
No.
Bras and cats.
Examples of row vector and column vector? Yes. So we reached any questions about anything we said? It's absolutely crucial that everything will be positioned properly in your mind before we move on to the next stage. Before we start doing, because this is still very simple. Believe me, it's very simple. So what is a gradient d phi? It's the partial derivative of phi, right, with respect to the coordinates, dx mu. I have to put here a theta mu.
Is it a form?
Now we can use the chain rule, right? So what is the chain rule? So use the chain rule.
Why is it theta and not E?
Let's do that in a second. So what is d phi? Dx mu prime. It's dx mu over dx mu prime. D phi over dx mu. Right? What is dx mu over dx mu prime? What Lorentz transformation is that?
Upper mu and lower
What? It's the inverse Lorentz transformation. Right, so this is lambda mu prime mu d phi dx mu. I take the inverse Lorentz transformation because I have the old one with respect to the new one, not the new one with respect to the old one. Right? What does it mean? That's the inverse Lorentz transformation, which means that the gradient, oh, I didn't say it. A covariant vector, another name is covector, another name is a dual vector. There's many names. It's also called one form. Right? So the gradient is a dual vector. Now, of course, you don't see that in Euclidean space. You're used to think of a gradient as a vector, right? You're taking a scalar and you turn it into a vector. No, you turn it into a covector. You see it very clearly in non-Euclidean spaces. Yeah.
We said vectors belong to a point, right?
Yeah.
So, and the scalar function is defined as all space, right?
Yeah.
So
yeah, I'm cheating here.
It means
I didn't show you exactly how do I take. No. Sorry, for a gradient, there's not a problem because I'm taking the derivative of that function at that point. Yeah. For the gradient, there is no issue. But if I want to take the derivative of a vector, that's a different story.
But well, if you're taking only at a certain point,
yeah,
a gradient isn't. It doesn't exist for a function that's defined only in a single point. It needs some environment at that point.
Yeah.
Some neighborhood at that point.
I need to think a little bit about that.
You need to take some limits.
You're right. I need to think about that. Maybe I'm cheating a little bit. I have to think if I'm cheating here or not. Okay. You got me. I have to think. Yeah.
Just for convention, it's because it's a derivative that you treated the index as though it's on the bottom.
Yeah, that's the definition of a gradient.
What's it?
That is a definition of a gradient.
No, I'm just talking about the Einstein convention. In the definition of the gradient, it's a little bit different than what we saw till now. No,
it's not different what you saw.
No, above that.
Which one?
Okay.
That one?
Yeah.
Yeah. That is a way of. That is my notation. That's a notation. Actually, I'm going to get you even more confused in a second. And right now it's the second. So because the gradient is a covector, so I'm going to switch these terms without thinking. Covector, dual vector, covariant. One form I will not use because we're not doing P forms here. But okay, so the gradient is a dual vector. And the convention we're going to use, again, because we have to confuse you a little bit more, so when I have d phi over dx mu, I'm not going to write all that, because that takes me too long. This is equal to d mu phi. This is the notation. It's a standard notation. So d mu phi means d phi over dx mu. And an even shorter notation is phi, comma, mu. That's it. That's it. We don't need more. Phi, comma, mu is the derivative of phi with respect to x mu. Okay? Get used to it. It takes you a little bit to get used to it, and after that you cannot understand how you work without it. I told you we're learning a language. Okay? Thank Einstein for all that if you want, but remember that. And you'll occasionally see me doing that. Actually, occasionally you might see me just doing this semicolon like that, but we'll explain what the semicolon is. Right now we just do the colon. In a sense it's easy because you have this x mu, which is a vector, right? And it has an upper index, but it's in the denominator. So I put the mu down. I'm using the denominator.
But it doesn't work for any time it's in the denominator, right?
It does work for what?
Does it work for just 1 over dx or 1 over x?
Right, it's enough. The phi over the x mu.
No, I mean other than in the derivative.
Slowly, one step at a time. Don't jump. One step at a time, we get it all. What happens when I take the gradient, which is a dual vector? So I can operate it on a vector, right? What happens when I operate the gradient on a vector? So if I have a vector that is defined along a curve, right? So if I have v, which is v mu e mu, right? And v mu, I define it along a curve. So it's dx mu over d lambda, vector tangent to a curve. So what happens when I take the gradient of the function phi, d phi, or some v? Right. It's a d mu phi that works on dx mu over d lambda. What do we get? Come on, that's easy. Of course, phi over d lambda. Very easy. Nothing else you can do really. The nice thing about the things is that you don't really have options. Once you get used to that, it's like that's the only thing you can do. You can't really get lost. Okay. So, do you have any questions? Yes.
Don't we need to embed the manifold in some space to
No.
define
No.
the curve? The curve.
The curve is defined on the manifold. The manifold is self-defined.
Yes,
The manifold is the space.
But to define coordinates, the coordinates of the curve, to parameterize the curve.
No. No.
So what's the definition of x mu?
Again,
of the
it's a
curve?
local coordinate. It's a local coordinate. The manifold is the space.
Okay.
I do not need. I mean, you can think of the surface of the Earth and you say, "Hey, Earth is okay." I agree that the surface of the Earth is and this is the thing that I should have put more emphasis on. Right? We live in the surface of the space, right? Airplanes that fly, no, they're fixed. You know, you have a certain height that you can fly above the surface of the space and of Earth, and that's it, right? Think of us in terms of ants. We are ants. Okay, if it looks strange to you, think of the universe. We are ants in the universe. Okay. Now we don't have a way of getting outside of the universe. Like today, okay, we can send astronauts to the moon, and they can watch Earth and say, okay, Earth is round. But as an ant, ants cannot do that, right? To the best of my knowledge, right? Ants do not send spaceships. Now think of an ant called Gauss that say, okay, I can deduce that the space that I live in is not a Euclidean space.
Okay.
How do they do that? So
Some sticks in some places.
that's what we are. And if it sounds strange to you, right, again, think of the universe. We cannot send a spaceship outside of the universe to look outside and say, oh, the universe is whatever, round, flat, whatever it is. Right? We cannot do that.
My question is.
Wait, again, the manifold
Yes.
is the space.
Okay.
Since we're physicists, we're not limited to Euclidean space. We are limiting ourselves to nicely behaved manifold, as I said. So nicely behaved spaces and nicely behaved. There is a mathematical definition. I'll give it to you if you want. There's no problem. Right? It will just take half an hour to go through because you have to make many definitions. You know, what is an atlas? What is several things that we need to do. What is a chart? What is an atlas? Open group. Again, it's not crucial to understand. Crucial to understand, a manifold is a well-behaved space. Well-behaved, it doesn't have spikes. Okay, it's not a space that have. This is not a manifold, right? But curved is a manifold. It's well-behaved in the sense that at every point inside this space, you can always find a small enough region, epsilon around this point, in which this space resembles a Euclidean or Minkowskian space. Okay, that's what I mean. You always have, if you take a magnifier lens, you look close enough, it looks flat.
Yeah.
Point.
My specific question is, how can you denote the curve by x mu?
No. The curve I denote by lambda.
Lambda?
Yeah.
Okay.
No, the curve I denote by a different name. I call it my trail day one.
Okay.
Okay? My trail day 1. I now take my backpack and I go on a hike.
Okay.
Okay, I like to hike, so I go on a hike. This is my trail, day 1. Now I show it to you on the map so that you can find me. And then I tell you, okay, my trail, I will be going along this trail. Okay? And how do you know where I am? You know that I'm somewhere on this trail.
Because of the time.
Now I need to parameterize where I am on that trail. So I parameterize it by, I split the trail into little bits and pieces, and I mark them with numbers, right? And I call this lambda. So this is lambda equal to 0, this is my starting point, lambda equal to 1, lambda equal to 2, etc. This is how I define my trail. Now for the coordinates, at every point, in every manifold that I'm in, since if I look close enough, I zoom in to this point, it locally looks Euclidean. Minkowskian, right, if it's 4-dimensional, but for my trail it will look Euclidean. Right, doesn't matter where I am. If I look close enough, it will look Euclidean, right? If you magnify, it looks Euclidean, right? Then I can always find a set of Cartesian coordinates, right? Which I call them x mu. That's all.
Oh.
Okay? Good. Now, more questions? Okay? It's abstract. So that's why you have to think of it. I'm very worried if you don't think of it, if you don't ask questions. But normally, by the way, I don't know if... how many of you read Feynman's book? Surely you're joking. Feynman, Richard Feynman, D. Feynman. You should go and read. He says that, right? Which one of them, right? Feynman's there. There's Feynman's lecture, but not that one. He says, ask questions. There is a strong correlation between those who ask questions and those who understand, and you don't care, but those who get the higher grades in the final exam, and that you care. There will be a final exam. You won't get out. Right? So there is a correlation. You must ask questions in order to understand what's going on here. Okay? And don't think the question is stupid. It is not. Right? As a rule of thumb, if you don't understand something, make sure. I'm sure that there is at least one more person in this classroom that doesn't understand it. Hopefully it's not me, but I can't guarantee. Okay, make sure that every point has to be clear. Yeah, had a question?
About the kind of more formal, concise definitions. Do you have it on your website?
Yeah, I told you, everything's there. Besides, go to the textbooks. Off I gave you, there's a full list of textbooks there at various levels of difficulties. The first ones are the easier ones. Then it goes harder. But there's no shortage of textbooks in there. Okay, let's move on beyond to the next subject and start with it. Tensors. If we now explain what is a vector and what is a covector, what is a tensor?
It's a combination of the two.
What?
Some combination of the two.
It's when you multiply.
Let's be a little bit more mathematic.
It takes as a function a bunch of vectors and a bunch of dual vectors and gives a scale.
Very good, right? So, formally, if we say, so let's write this down, right? So formally, tensor. A dual vector is a linear map from a vectors to R. So it's going to get formulated abstract. So a tensor T of rank KL. That's how we sign KL. What is that? I want to say type or rank. Type. is a what?
Abstract.
Is a multilinear map of what?
K vectors and L
Of a collection from a collection of what?
K
No, K what?
K covectors.
Of K covectors and L vectors to R. That's a formal definition of a tensor, rank KL. What does it mean, multilinear?
Linear in each component.
Linear in each term. Okay. That means linear in each term. Yeah.
Try to explain what it means linear in each term.
Yeah.
What it means.
Let me see that in a second.
Okay.
Okay. So what is a scalar? You asked me, what is a scalar?
Something that stays invariant.
What is a scalar?
Number.
Type?
0,
0, tensor, right? Scalar? Scalar is a tensor of type 0, 0. What is a vector?
1, 0. What? 0.
Vector
And switch.
is a tensor of type 1, 0. Covector,
0, 0.
vector, 0, 1. Everything is a tensor. I'm going to answer your question in a second.
You said the opposite. Covector is the K.
That's the number of upper indexes, this is the number of lower indexes.
But you said K covector. Okay.
Yeah? I said correct. So that's correct. What?
So the number of coordinates should be
I said it correct. Just a few more things, and then we answer that questions, and then we see how to proceed. Like I go home. לא, מדויק, אין פה טוב. הכל בסדר. Transformation law of a tensor. So a tensor of rank KL would essentially have K contravariant indices and L covariant indices, right? So we can write a tensor, transformation law T, mu1 prime, mu2 prime, mu K prime, and then mu1 prime, mu2 prime, mu L prime.
When you put a sig, it's a derivative.
Here there's no.
Okay.
Here it should be clear that there is no derivatives here. Okay. You're right. And each one has its own space, right? You don't put anything above or below each other index. Each index has its own space. Okay? Is equal to what when I make a transformation? Oh, I see that. Let's put no, it's okay. How do I make a transformation of the tensor? Component by component. Right? Component by component. What do I do with the upper ones? Each component transforms like a vector. With the lower ones, like a covector. Very simple, right? So it will be lambda mu1 prime mu1 lambda mu 2 prime mu 2, lambda mu k prime mu k, and then multiply by lambda mi 1 prime mi 1, lambda mi 2 prime mi 2, lambda mi L prime mi L times t mu 1 uk mu 1 mu L. Maybe. Any upper index is transformed like a vector, any lower index is transformed like a covector. Give a few examples, then I'll check that I answered all the questions, and then we can go on.
The order doesn't matter because it's a summation, right?
The order matters. I mean, here it doesn't matter. I mean, you can switch the orders of these ones, because you're doing one by one. But this rho sigma nu is not equal to this sigma rho nu. They're not the same. Don't start playing with the indices inside the tensor. When you're multiplying here term by term, because there is a summation here, remember, right? There's a summation. You remember that, right? All the mu's and the nu's. Then you can switch the order of the terms, because you're summing over them anyway. You multiply. But for the tensor itself, not there. Okay, so there is one tensor which you know.
The metric.
What? Metric tensor. What rank tensor? What rank of tensor is that? What?
0, 2.
0, 2. So example. The metric tensor. That's the true name of that, right? It's not just called the metric. It's called the metric tensor. Is a 0, 2 rank tensor. Right? Hello at that unit. Right? It has two lower indices. Now, which means if it's a 0, 2 tensor, then what? It can take two vectors and turn them into real number. Didn't use the term scalar. Actually, I did use the term scalar. Scalar is a tensor of type 0, 0, right? So eta takes two vector, v and w, right? Turns them into a real number. Now this is so important, it says its own name. You may know that. You know, what's the name of that? Inner product. That's called inner product. This is called inner product.
In this case, it is a scalar.
It is a real number. Yeah. A real number is a scalar. Generally, yeah. So, but it's important that you follow the notation. So this is equal to eta of v and w is eta mu nu, v nu, w nu. Yeah. That is also being written as an inner product, v dot w or w dot v. That's not automatic, right? Why did that follow? That I can write that?
Symmetry.
The symmetry, right? Because eta is symmetric when you exchange the two indices. Right? There's only things on the diagonal, but there's no above and below the diagonal. Everything we're going to get in this course is going to use symmetric tensors like that. But tensors are not generally symmetric. In a little bit more complicated environments, such as rotating black holes, then the tensors are not going to be symmetric. What is that? This is equal to what? Let's see, what is eta 0, 0?
A minus.
Didn't forget it, right? Minus v V0, W0, plus, right, eta 1, 1, plus 1, V1, W1, plus V2, W2, plus V3, W3. Yeah? Now, we're going to stick to the same notation that you're used to. So two vectors whose inner product is 0, how do we call them? Orthogonal, right? So if eta VW is equal to 0, we say that V and W are orthogonal. Of course, the dot product R is a scalar, so it's invariant under Lorentz transformation. So, for example, if we take basis vectors of Cartesian coordinates and we Lorentz transform them, they will still be orthogonal to each other. So, do that for a second. What is the norm of a vector?
Square of the inner product of the set.
That's right. So we say that the norm of a vector V squared is eta mu V mu V mu. Or now I can use the metric tensor, that's the only one, metric and the inverse metric, only two, I can use to lower and raise indices. So eta mu nu V mu is V mu. Yeah.
How do you know that it's V squared and not the second part?
It's what? Not the what?
And not the power שני של כאילו לא ה-component.
You don't know. You have to understand it from the context. Yeah, it's a malfunction in the notation, you're right. Yeah.
It isn't equal. Isn't equal. Like
What? I don't
V
understand.
mu.
Definition mu.
No, the right hand side equation. Yes. Oh, you
Eta
can say
mu
that's,
mu.
this is the definition.
Yeah, I can use the metric tensor to lower index of a vector. Only the metric tensor. And the inverse of the metric tensor to raise. Okay? I didn't say